presentation, go.
So I'm presenting on the facial intermolecular activation of a hydrogen-carbon bond in methane and other hydrocarbons in sealing with the iridium complex. So this was a research done by Peter Berger and Robert Bergman. Both at the time were working as professors at California, Berkeley. Peter Berger is now a current professor at the University of Hamburg, Germany. So basic oxidative addition of a carbonyl. This is a very major process in organometallics. They're trying to activate the hydrocarbon. Most of the time this bonds to the rich electron center of a metal. So this normally happens with your later transition metals due to the higher d electron count. So most of the later transition metals have a lower oxidative state, +1, +2, sometimes +3. And so that's what Berger and Bergman looked at, is the iridium +3 complex. So this is just a basic mechanism for the iridium 1. So it still has 6 d electrons, so it still has the ability to easily bond into the carbon and then activate that hydrogen-carbon bond. So priorly they looked at a research by a guy named Schlave. He did some research on iridium-2 complexes, and so his basic mechanism was that it still had enough d electrons that it would bind and activate the carbon-hydrogen bond. His proposed mechanism was a little bit different. He used the 2 methyl groups instead of Bergman and Berger. They used a OTF compound instead of where one of the methyls are. One of Schlave's research looked at the addition of the benzene ring. And so the first step, it would add into the benzene ring, but also you would get this nucleophilic attack of one of the methyls back onto the phosphine groups. So Bergman and Berger, they looked at metals such as iridium and ruthenium, and stated that they were one of the few late transition metals that had the ability, even with a higher oxidative state, to undergo this attack on the carbon through the intermolecular sigma bond metathesis exchange. And they also looked at intramolecular sigma bonding. They proposed that this high oxidative state, even though some of the electrons were gone, still give the metal to act like an electrophile instead of like the early transition metals did. So this is their scheme 1 for their iridium complex. They proposed that while the iridium would undergo the same type of activation, there was a large amount of steric restriction. So like in scheme 1, they looked at the proposed idea that for 3, it only occurs, which is here, it would only occur in the para and meta positions. So the ortho position was closed off by the large OTF complex, which would, for the iridium 1 complex, it would still have enough d electrons to move it to the ortho position. They also looked at the idea that for step 4, that it was not a direct bond into the carbon, that there was a steric interference by shielding with the 2 methyl groups on the outside. They also looked at through 1 that neither the cyclohexane nor the neopentane would undergo a reaction. They believe that this was due to the large steric clash between these two molecules, that the methane was more desirable to stay bound in than the cyclohexane or the neopentane was. They did observe that benzene would react, but it would only do it at higher temperatures above 100 degrees Celsius. And then they did some work for the carbon labeling, which is at the top. They carbon labeled to see exactly what positions the methanes were bonding in at. They did propose that once the methanes bound in, that you would have the ability to add in another higher electrophile or nucleophile, and it would remove the methyl back off. For the silanes, they were expecting a direct addition, and that was not the case. Instead of having, say, for the first one, the bond would go to where the hydrogen was in the silane, it actually pulled off one of the methyls first, and then added into the silane complex directly to the silane. For the phosphine group, it does the same thing, except it strips off the methyl and strips off one of it strips off the methyl and strips off the phenyl groups. It strips it off and adds it to where the methyl position is. This was key in that they proposed that it would directly bond in, and so they were getting compounds that were a mixture of both their original product and their starting material, because it would keep bonding back to this, stripping off this silane and rebonding back to this methyl. They did say that there was even large steric restrictions on these. Because of this OTF compound, it would strip off itself and go and bind to the silane, which would close off some of the binding area and restrict where it bound in the position with the iridium. They proposed a general mechanism, so they were trying to understand whether or not when the OTF was pulled off, whether or not it was just a direct ionization or whether it was part of the stripping. It was stripping some of the electrons away from the iridium complex. And so they proposed this first step being the ionization of the OTF and the iridium complex, which is seen here. And then they looked at the direct addition, which is step A, and proposed that it was a signal bond metathesis. So it was a direct addition in before the methane come off. So the methane would actually agnostically bond to the hydrogen of the new carbonyl, and then that bond would be broken to add the carbonyl to the iridium complex. Then they stated that it was a direct cleavage oxidative addition, so they would just directly cleave this bond and would directly bound the hydrogen and the carbonyl to the iridium. And then this new methyl, the methane would then strip this hydrogen off, and you would be left with your original iridium complex. They did look at the silanes, they looked at it being a direct addition, when in fact it stripped off one of the carbonyls from the silane and added it as a double bond, because this would be more of an electrophilic attack, electrophilic attack. And then the OTF would come back in and strip off, break this bond and add back to the silane to give you a neutral charge. And that's about it.
Okie dokie. Questions?
Were these all three
recognized mechanisms, or was it one was preferred, or like anything like that?
They proposed that it was more of the B step. They said that they could, depending on the R group that was added, that this could happen. They looked at the idea that like they didn't have the beta hydrogen to do this step, then it would just go a direct bond. It would just cleave this bond here. They did state that they couldn't actually get this complex. They couldn't isolate it to determine if that was there or not because it was such a fast breakdown. That they proposed that sterically the R group would determine if it went the A path or B path.
For 11 there, what's your electron count?
The D5. Wouldn't it depend on what this is though?
So R is going to be anionic because you're either going to be cracking a silane or a carbon. In this case, it's going to be a carbon. So assume it's going to be a negative charge.
Okay. So would it be D6? So 6. 16 electrons?
Let's see.
Does have that plus on it.
Yeah, it does have the plus. So the oxidation state of that iridium is currently what, I guess, for number 11?
D6.
No. What's the oxidation state?
This +1.
No,
Or is your CP?
the plus is for the overall compound. So these things started as iridium 3 complexes, right?
Yes.
So-
it's
So what do we do if we undergo an oxidative addition? What has to happen to the oxidation? Goes up by how many?
There's a one.
I'm sorry?
It would be 4. Yeah.
One more?
5. Because of my
Plus
2.
Iridium 5, yeah. Because we're going to go up by 2 by adding that H and the R, because both of those are going to be anionic in this case.
Wait, the H is in it.
Mm-mm.
Didn't it start at 3 with 3 things on it, no? Wouldn't it be?
Yeah, because we already be a plus
So-
state here.
That is the +3 state, right?
Yeah.
So we have a negative from the CP, we have a negative from the CH3, and then we have an overall positive charge.
Oh, okay, yeah. All right.
And so when we add that RH, we're going to have to go to +5. So in that case, we have 5. So we have 4, plus 5, 6, 7, 8, 9, 10, 11, 12, plus 6 gives us 18 for 11.
What's the decount on?
So it's +5, so iridium is going to be D4.
Okay.
If you go back a couple slides to your, I guess, overall structure, yeah, there you go. So as everybody see, the CP star in this case, like we said when we were talking about the CP rings, CP star is bulky as shit. So right now the iridium is in what is a normal quote-unquote piano stool. So the CP star is the seat, and then you have the 3 legs underneath with the phosphine, the methyl, and then the triflate ligand. So imagine trying to add 2 things to that already extremely sterically congested environment. And so that's the rationale for why that cyclohexane and then the neopentane I was talking about, those aren't going to react because this molecule doesn't allow for close approach of anything that's bulky. It has to be something that's relatively small or something relatively pinned back, like those para-substituted benzene rings. Okay, go back forward to your mechanism that
So
you had.
in this step, like, can you explain, like, they didn't go into 4, but why does it bind, like,
Why does it make that allyl
Why
compound?
does it, because like the benzene, why doesn't it just add another, like,
So for the benzene, it's taken off one of the benzyl hydrogens because that's all it can do. And of course it can get relatively close since there's no methyls around it. For the case where you have that diparasubstituted xylene or
couldn't it go to
the
the
paraxylene.
what, ortho, or the, can still bind in to one of those hydrogens, or is that too tight?
I'm sorry?
Can it still not pull up one of these hydrogens here, or is that too tight of?
It's more that the methyls now make it harder to reach that hydrogen. And so what it does instead is it strips off the hydrogen that's off the methyl, because that's the one that's going to be able to actually close approach. And so that's why you end up with the allyl compound in that case.
Why wouldn't it just directly bind to the methyl one?
Like, why wouldn't it just go
Like if it
here?
strips the hydrogen, why would
Just
it
go straight into there.
So in this case, apparently there's, it's going to be, again, you probably have to do more studies, but it looks like it's going to be energetically favorable to do the allyl relative to the triflate coming back in and binding and kicking it off as more of an 8-1, if that's what you're saying. So instead of taking two of those bonds from the benzene ring, it could take them from the triflate anion coming back in, but apparently it's energetically favorable for it to do this. For the cyclopropane, that gets easily cracked and becomes the allyl group there. And then you can form an olefin from unsubstituted ethane for, is that number 6, I guess, at the bottom. Go forward to the silane one for me, or to the mechanism for the silane. So, okay, sorry, go back one. So everybody sees the weirdness involved with the silane, right? So you have this issue where the triflate is going to fall off, and then you're going to do the oxidative addition of that silyl bond, and then the hydrogen is going to get transferred to the CH3, and you're going to kick off a methane. Methane is being released in all of these reactions. And so in the top case, since it's a trimethylsilane, one of those methyls then comes back off, jumps on the iridium, and then the triflate comes back in to attack the silicon, or the silicon atom. And that happens for all of these. Now if you go forward, Hunter, the mechanism that they're suggesting for this is that the methane initially goes away, you form this bottom left compound where you oxidatively have added the silyl group, and then one of those R groups jumps off. And in one case it was the methyl group, in another case it was the phenyl group. But you form this kind of silene compound, which is interesting, this iridium-silicon double bond. And then the triflate comes back and attacks the silicon, and the electrons flip back onto the iridium. It's very strange, and they don't really explain it in the paper. If you go back one, Hunter, why they get movement of the groups that they do. So in the case of, let's say, 8 and 9, you guys can see that a phenyl group moves in both cases. So in 8, there's no choice, so they're all 3 are phenyl groups. But in number 9, you have a choice between either those 2 methyl groups or the phenyl, and it appears that the phenyl does it. It doesn't make sense then when you go to number 10, you have a choice between a phenyl and a hydrogen. Oh, then the hydrogen jumps instead of the phenyl. So they don't really have an explanation for which R group's going to come off. But most likely what they'll state is that they want to form definitely the hydride, because iridium hydrogen bonds would be relatively strong. You would think if it had a choice between the phenyl and the methyl, they would want to bond to the methyl, but it doesn't in this case. The phenyl jumps off on it, so it's kind of strange. I assume that they said they were undergoing additional studies for those. If you go back to your scheme 1, I guess, maybe? Was that it? Okay, no, sorry, go forward to, back to the mechanism, there you go. They also state that, they said that B, they think, was the predominant one?
Yeah, they stated that
Pathway B, I'm sorry.
B was a more predominant pathway, that it would give you, that they were trying to explain some of the reasons why the steric volt was involved, and that they were stating that this, like they bonded into here, then that would increase more steric volt versus this.
Okay. So they're saying that something was sterically bulky, that it would, if it were going through A, it would have a higher chance of occurring?
Yeah, there was like, if you were really bulky, you could do it this way, but
Uh-huh.
this the general, like when I look at the methane and stuff like that, this was the easiest pathway,
Okay,
because it could just directly bond in and then just shoot the hydrogen back out.
right, okay.
But if not, they were saying if they're really bulky, then you were already adding 2 more things
Mm-hmm.
and just increasing the bulk even more.
Right. So they're suggesting that B is predominant over A because they don't see those very sterically ligands get attached to it. Okay.
Yeah, because like I said, they tried with the cyclohexane and it wouldn't even bond. It wouldn't even get in. And then the benzene would only do it at higher temperatures.
Gotcha. And they follow, this was all mostly done by NMR, right? They did the carbon
Yes.
13 labeling for the methyl group. Okay.
Yep.
Did they ever isolate any other structures, or was it really just their initial starting catalyst as far as what they showed? Did they isolate any X-ray structures for the products?
They did
Or for any other intermediates, I guess?
For one, they did for the they did for the complex at the top. That's the only one that they tried to do anything other than NMR with.
The one with the phenyl ring on?
Yes.
Oh, they were able to crystallize that one out?
They got a percent, probably a percentage of 89%, so I guess that's the only one they found out. But they mostly did just the carbon labeling with the carbon 13.
Okay. I was just wondering if they were able to isolate an intermediate somewhere along the way as far as after it had added the substrate. But I'm guessing it's pretty reactive. It's probably hard for them to stop it there.
Yeah, they did say that in 311 that intermediate was, yes, this one. That they got this intermediate by,
Did they see that in solution? That they had, say, a hydride formation?
yes, they stripped all, they didn't allow they removed this methyl, and then so it didn't have anything else to bond back with. Just something to bond with. To strip the hydrogen back off.
So
They really weren't looking for intermediates, they were just looking at,
so they're just inferring
yeah.
these steps based on what they had to start with and what they ended with. Okie dokie. Thank you, sir.